Welcome to the next video of 3510. We're going to talk about DFS, which is also a classical algorithm to explore a graph. And what do we mean by explore? Well, we simply mean we want to traverse the graph, and while we do so, maybe we would like to collect some information about some basic properties. Properties that we defined at the beginning or in the first video, will be the beginning for this format, when we talk about general properties and notation, and we talk about connectivity. This video and the next one will focus on connectivity properties of our graph, and everything starts at DFS. So let me move into this algorithm. What do we get as an input here? Well, we are trying to explore a graph, and this graph could be directed or undirected. We will have no weights or anything like that. This is simply a graph. And the way I like to visualize DFS or any other exploring algorithm is as me placing myself in a vertex and looking at the graph as my universe, and I am trying to move around. And when I move around in the universe, I like to keep track of things that I do. For example, I like to know where I can reach if I walk through the available path, which will be edges, or path made out of edges in this case. I would like to know if I can reach a vertex, if I would like to know how I can reach that vertex or a path that will connect me there. And we will introduce other notions like topological sortings and strongly connected components in the directed case, but that will happen later. Today, we want to focus on depth first search, which is what we call DFS. And what we're going to do is we're going to present an implementation of DFS. We're going to discuss what properties we can get out of that implementation, and we will move to the directed setting in the case where the graph is directed, and we will also present an implementation that incorporates a couple of details that allow us to get deeper property, or perhaps not so trivial properties of the graph we are exploring. DFS is very intuitive. If you need to explore certain universe or a city or any setting that you have in mind, well, you literally do that. You explore, and exploring involves this uncertainty that you don't know what's going to happen. So maybe one strategy could be you want to walk through the path that you have available until you cannot reach a further point, and then you maybe backtrack, and then when you find a new path, you follow that until the end, and then you come back, and you keep doing this until you have explored the universe, as I've been referring to the graph. And this is precisely what DFS does. And the wording, depth first search, is precisely to encode this philosophy. You're going to follow the path until the very end, and the end means you cannot continue along edges out of the last vertex. And when that vertex has been reached, well, you backtrack to that path until the first time that you can essentially find a new path, and then you will follow that new path until the end, and then you come back and you keep doing this until you have explored the entire I'm going to say graph, but that's not quite precise. We will make that statement precise soon. Now, this procedure that I describe vaguely and rather informal in words can be executed with this procedure that we will call explore. I took again this pseudocode from the book in case you're matching the readings with the videos. And this is just answering the question on top. Given a vertex V, what other vertices can be reached from it, or which other vertices can be reached from V? And we present this procedures explore, which receive as an input a graph. Focus for now on the undirected case, but you will soon see that there is no real difference in the directed case. But focus on the undirected case, and you will be given this graph and a vertex, and special vertex. And what we're going to do is we're going to use a label that we're going to call visited for every vertex in the graph. And we hope to make these labels visit for those vertices U that are reachable from vertex V. So how you can implement this? Well, you can start by setting visited of V to be true, because you are going to start your exploration from that vertex, so you will visit that vertex at the very beginning of times. And then for every edge in your graph out of vertex V where you are and connecting to vertex U, what we're going to do is we're going to check if we already visit vertex U. If we haven't, if not visited U, then we want to explore. We want to call the same procedure at vertex U. And otherwise, well, you have seen this vertex before you just loop back to another edge out of V. A few things to notice here is I, on purpose, skip mentioning these pre-visit and post-visit variables or whatever you want to call it, because these are going to be like sub-procedures, if you want, that we're going to use to our benefit soon. So I skip them for now. And the other thing that is maybe worth to mention now, and we're also going to come back, is the idea that with this procedure you will traverse every edge once, and exactly once, because you will get to that edge at one of the endpoints, either B or U, and you will follow that edge to discover or to visit for the first time the other vertex, and that's it. Once you have done that, you don't really need to revisit that edge, at least in a meaningful way. I want to say that idea now because later on I'm going to mention that again. Let me summarize the discussion we just have using some bullet points here. First, this procedure explores all the vertices that are connected to V, and this is what we define as a connected component of V, all the vertices you can reach from V. Again, I am focusing this discussion so far in undirected graph. Now, the second idea is that the running time of this procedure is linear in the size of the graph. In other words, in the size of the number of edges plus the number of vertices. It is important to make this distinction, and we will always do that when we will discuss running times for graph algorithms, because the number of vertices and the number of edges, they can have different growth in terms of the variable that you choose to label this. Typically, we will label the number of vertices with n and the number of edges with m. You know that in simple graph the number of edges is at most n squared, but that is a square of the number of vertices, so we want to emphasize how both quantities are involved in the running time. Now, I hope you can agree with me that the procedure explore runs in linear time, the worst case. A worst case is that you visit every vertex in your graph, so you need to label every vertex as visited, and that gives you a linear time in V, and you visit every edge exactly once, which is what I was telling you before, and that gives you also a linear time in the number of edges. It may be misleading, this for loop nested with this if condition, because you may be tempting to think that you need to multiply the number of edges, which is kind of the length of this loop, times the number of vertices, but that is not accurate. The right idea is the one that we discussed before, that says that you visit every edge once, and once you label the vertices as visits, you don't really have to explore anymore from or to that edge. And another important idea which we mentioned, but I want to have it in paper or in a slice, I guess, is that we have these two procedures, pre-visit and post-visit. Both are going to be things we're going to use to our benefit, and you will see that very soon in this very own video. And these are going to be optional. You don't really have to use it unless you want to get something out of it. And since we will be using these algorithms as black boxes, most of the times you not even have to worry about clarifying how you're using these procedures. You can simply mention, I'm going to use DFS or explore to get this outcome, and then I'm going to use that outcome or this output to get a solution to my problem. We will discuss more about this black box use during the live sessions. So pre-visit and post-visit are these procedures that happens once the first time a vertex is visited, and the other one right after you finish exploration from the vertex. Now, DFS, the algorithm DFS, is what you do if you explore the entire graph. In the previous slide, let me go back for a sec. We're doing the exploration from vertex V, and that means that you will only explore those vertices that are connected to V. But your graph may be disconnected. DFS is simply looping through all the vertices and doing explore from every vertex. So you start by setting every vertex to be visited equal to false, and then you simply start exploring the graph. You start at any vertex V, and if you haven't visited that vertex yet, you explore the connected component of that vertex. You explore from that vertex. When you are done doing the exploration of that component, you will jump to the next vertex in the order or the sorting that you predefined it, and you will repeat. I will show you an example very soon, so no worries about this. Now, it is important that you will fix an ordering of the vertices to decide, for example, when you finish exploration of one vertex, what is the next one you're going to explore. And it's also important to decide which edge you will explore first when you do the exploration procedure. Because you see you have a loop through all the edges that are adjacent to a vertex. It is important to choose which one will come first or which one will come after. It's not really relevant first, for now, it's not really relevant how you fix this ordering of the vertices. We will talk about precise applications in which it will be very important to have a predefined sequence of vertices, or in a predefined order, the vertices. Now that we have this discussion about the implementation of DFS, and I hope you also agree it's fairly simple to implement DFS, let's talk about some applications or some things we can get out of this algorithm. These are the type of things we will use as black boxes, so you may want to take note of these possible outputs. One first idea is, for example, you can find a path between two vertices, given that these two vertices are in the same component, of course. You can even say, if you don't find such a path, that these two vertices will not be in the same component. One way to get a path connecting two vertices is by pre-recording, or in the pre-visit label, keeping track of the vertex you are coming from. In other words, you keep track of the vertex V such that the edge VU leads to the first visit to vertex U. If you do so, it is obvious that backtracking through those vertices will take you back to the initial vertex in your component, and that describes a path connecting the initial vertex V in the explore procedure to the vertex U you wanted to connect. Notice that this is very specific, that saying that we have found a path connecting these two vertices. There could be many paths, there could be actually exponentially many paths. This is not the shortest path because this is DFS. So there is no real extra properties here beyond the finding a path connecting two vertices. But there are many instances in which this is very useful, and I'm pretty sure you will discover those either in the list sections or in the homeworks. Another interesting application is to determine the number of connected components in an undirected graph. I told you that DFS is the algorithm that explores the entire graph, while the explorer procedure that is used in DFS explores a connected component. So we can keep track of the number of connected components and the connected components itself by setting a clock or a variable that I'm going to label CC because of connected components, and I'm going to start that at 0. And now in the initial visit to a vertex V, I'm going to update the vertex ZC, or the variable CC. I'm going to increase that by 1, and I'm going to explore that vertex. And notice that this update, the update CC, will only happen when you visit a vertex for the first time in this outer loop, in this for loop outside here. Now you can, in the pre-visit procedure, you can assign, within the explorer, you can assign a label to the vertex that you can label in any way you want. I use it ZC_num, and you just save the current value of the CC variable. So you initiate this CC at 0, you update this in the outer loop every time you visit a vertex for the first time, in the outer loop, in the for loop. And every time you go and explore, you simply set a value, the current value of CC, to be equal to this CC_num of every vertex. And then when you finish, you can output the vector of CC numbers. There will be a vector of length n, the number of vertices in your graph. And then I'm going to show you that every vertex will have a number that corresponds to a connected component. And every pair of vertices with the same number will be in the same connected component, will be connected. And of course, the maximal value of that vector is the number of connected components. Thus, how we can get track of the connected components and the number of connected components. Let me show you an example of this. Say that this is my graph. You can, of course, immediately see that we have 3 connected components. And according to the previous slides, I will set ZC to 0 at the beginning of times, and I will start exploring my graph or visiting my graph at some vertex. Say that this is my first vertex. I used a rather small label, apologize for that. I hope you can see is this vertex down here. Now, when you visit that guy for the first time, you immediately update the CC variable to be equal to 1. So now CC is equal to 1 and you explore. Notice that you are not in the outside for loop, you are exploring from this vertex. So you will see maybe this other vertex, and then you come back, and maybe you see this, and then you go here, and then you go down, and maybe you go here, etc. But you will finish in exploring all these vertices that are connected to the initial one, and all those vertices will get a CC value equal to 1, because you haven't updated the clock while you do the exploring. Now, once you have finished this exploration, you go out in the for loop, and you start checking whether the next vertex in the ordering you have, in any data structure that you're using, the next vertex has been visited. When you find a new vertex, one that you haven't visited, then you update CC. Say that you found this guy. Now you update CC to be equal to 2, and then you label the CC number of this vertex to be equal to 2. And then you proceed to do the same. You keep exploring the connected component of that vertex, and that will take you to visit every single vertex in that component and labeling the CC number of every single vertex in that component equal to 2. Once you have done, you will continue in the for loop until you find the first vertex not visited yet. Then you update CC again, you get number 3, and then you label the CC number of that vertex to be equal to 3, the current value. Again, you explore the connected component of that vertex in some order, depending on the ordering you choose, and you will label everybody CC equal to 3, CC number. At the end, if you output this vertex, you can immediately identify vertices in the same component to be those with the same CC number, and the higher value in that vector will be, in the coordinates of that vectors, will be the number of connected components. If you only have number 1, that means your graph is connected, for example. These two are simple applications of DFS. Through the course, through this segment of the class, I hope you will discover many others that will always be somehow connected to the connectivity properties, pardon the redundancy, of the graph you are exploring. But this has been set on the undirected case. Let me jump to the directed case. So now we're going to see DFS on directed graph. And let me start by mentioning that the implementation is, you saw something that is coming soon, the implementation is essentially the same, because nothing tells you that when you followed an edge in the explore procedure, let me show you that pseudocode, when you follow this edge, you only have to make sure that the edge has the right direction, it's going from V to U. But that's the only thing that changes when you look at the directed graph. If you have an edge pointing towards V, you don't follow that edge to explore, because that edge does not allow you to move from V to vertex U. You have to respect the ordering of the edge, the direction of the edge. But that in the implementation, that is the only difference. Now the thing is that directed graph are slightly more complicated than undirected graph, and we need to refine certain ideas in order to get properties of directed graph. Before jumping into that, I want to show you the word of the day. Is raton, which is the picture you're seeing. There are 3 types of ratons in this picture. We have ratons in Cuba, of course, but there is a bigger raton in Cuba. It's a relative of the raton, which is called jutia. And ratons are smaller, but jutias are bigger. They live on trees, and they are endemic of Cuba. So if you need a reason to go to Cuba, and maybe you need one these days, there you go. You can say that you're going there to study the relative of the raton. But the word of today is raton. Now that you have the word of the day, let's move to the implementation of DFS in directed graph. We want to understand connectivity properties in directed graph, but these are subtle, these are slightly different, because the direction of the edges tells you that you move in one direction only. So if you are thinking that being connected means having a path between 2 vertices, you want to double think that, because you have a path, that means you have a direction, you're going from one vertex to the other. But maybe you cannot come back, because that means you need to use other edges, very likely. Or a subset of those edges you join with other edges, but definitely you need to do something different. Another thing is, for example, a cycle in a directed graph have to respect the directions of the edges. So not any consecutive sequence of vertices connected are a cycle, because you need to respect the directions of the edges. I'm going to show you an example very soon to visualize these ideas. But let me introduce a couple of things we're going to do in these procedures pre-visit and post-visit. we're going to incorporate two labels to each vertex. We're going to put, again, we're going to put a clock while we implement DFS, and we're going to keep track of the times at which we see a vertex for the first time and we start exploring the vertices you can reach from that vertex. And we are also going to keep track of the last time we visit that vertex. And to do that, well, we use a clock and we will record the times during the pre-visit and post-visit procedures. Okay? Now, these first time and last times that you visit a vertex, they are very much related to a way you implement, typically, you implement DFS, which is using a stack. And this is precisely, these times is precisely the interval, if you want the times, that you spend on those, let me say it precisely, on the tree coming down of that vertex. But no worries about that wording. We will talk in details about those things. Now, how we can do this? Well, simply we have in the pre-visit of vertex V, we set a label that we're going to use the notation pre of V to be the current value of the clock, and we immediately after that we update the clock. And when we enter the last time, we visit for the last time that vertex, when we close the explore procedure of that vertex, we set a pause label to be equal to the current value of the clock, and then we update the clock one more time. The clock, if you want, is time moving, and every instant of time, every moment in time, something is happening. You are either visiting a vertex or exploring a new vertex or doing something in DFS, and you're keeping track of all these important moments. Here is the example, and maybe the best way to visualize this is by actually doing by hand the DFS in the directed graph. Before jumping into the implementation, let me tell you about the cycle idea that I was mentioning before. For example, focus on vertices E, F, and G. You do have edges connecting those vertices, but that is not a cycle, because a cycle must respect the direction. So if I start at E and, for example, move to F, that is a valid move because I move from E to F following the direction of the edge. I can also move from F to G following the direction of that edge, but I cannot move from G to E. And in order to have a cycle, I want to do that move. I want to move in order. So this is not a cycle. Now, B, E, F is a cycle because you can see that you can move from B to E, then to F, and then back to B, following the directions of the edges. That is a cycle. And then you see that maybe detecting a cycle is not so obvious. You need to somehow respect the direction of the edges. But of course DFS does that, so we should be able to extract that information from the implementation. Now let's see DFS on this graph to the left. The ordering of the vertices is the alphabetical order, so that means I'm going to start at A, and every time I have to decide, I will take the vertex that is closer to the letter A in the alphabet. The picture to the right is the final outcome of the implementation of DFS. The two numbers next to each vertex corresponds to the labels pre and post, and I will maybe fast walk you through the implementation, but I strongly suggest you to do this by hand yourself in a piece of paper. I will also link to the video of Dr. Bigoda on Udacity, because he also does an implementation of DFS perhaps slowly or slower than me for sure, and that may be also a good idea to watch. But then, as I told you, you start at vertex A. At the very beginning of time, you label the pre-label of A to be equal to 1, which is the initial time. Immediately after that, you update the clock to be equal to 2, and then you start exploring from A. The first edge we explore is AV. Once we land on vertex V, this is the first time we're entering vertex V, so we label the pre-label to be equal to 2. Sorry, pardon again the redundancy. You update the clock to be equal to 3, and then you explore from V. The first edge from V is, and also the only one, is going to vertex E. Again, you set the pre-label to be equal to 3, and you update the clock, and you continue the exploration. When you decide between the edges out of E, you go to F, which is the smaller one in the alphabet, and you get a pre-label of 4, and then you update the clock. You go down to G, you get a pre-label of 5, but notice there are no edges out of G, which means that when you explore from G, you do nothing because there are no edges. That effectively close the procedure explore from G, and then you label the post label of G to be equal to 6, the current time of your clock. Right after that, you immediately update the clock to be 7, and you go back to F, which is the edge. Oh, sorry, this is the edge you're coming from, and there is another edge that is taking you from F to V, which is marked as discontinued lines here in the picture. You do nothing because you have seen V before, so there is no update of the labels. This is part of the exploration process from F. And once you are done, because these are the only 2 edges out of F, you also label the post of F to be 7, and you update the clock, and then we continue doing so. We continue moving along the graph, following the alphabetical order, and until you finish the whole implementation, which take you to this picture on the right. I strongly suggest you to do this yourself, maybe in a slow pace. And if you guys are you feel like you need to see this in class, let us know, and maybe we can do this once in the live sections. Given this, let's try to extract some information out of all these things we have collected, these pre and post labels, and the structure of this exploration process that you have to the right. Notice that it looks, at least on paper, it looks slightly different to the graph, the initial graph that you have, although it's the same thing. We're going to get some info out of these numbers. Let me notice a couple of things. For example, the pre and the post labels are always between 1 and 2n. Why is that? Well, because we update the clock precisely twice per every vertex when we do the pre-assignment and the post-assignment. Since we have n vertices in total, we will have 2n updates of the clock, and those are the values of the pre and the post labels. So these inequalities holds true for every graph. Also, the interval defined by the number pre of V and post of V is the amount of time you spend on the stack. And because of that, you can conclude that these intervals are either nested or disjoint for every pair of vertices. This is more of a property of the implementation. We may not rely too much on this, but for certain problems, for certain applications, it's actually nice to have it in mind. And in particular, you can conclude that if the interval pre of V, post of V is within the interval pre of U, post of U, then the vertex V is a descendant of vertex U. What do I mean by a descendant? That means that we explore U first, we went down the edges, and we found V in the process. So V is a descendant of U. That terminology will be even more clear when I move to the next slide, which is classifying the edges of my graph dependent on how they appear on the DFS implementation. Notice that this classification depends on the ordering of the vertices you have. See, if you change the ordering of the vertices, maybe the label of each edge, the classification of each edge will also change. So these categories that we're going to define relies on the ordering of the vertices. It's completely fine if 2 students use the same graph but different orderings, and they get different DFS processes, and because of that they get different categories for the edges. But the category will tell you the role the edge is playing in the implementation. And the first one is what we will call a tree edge. What is a tree edge? I gave you a couple of examples, a V and FG. These are edges that takes you to a new vertex, to a vertex you see or you visit for the very first time. When we explored the edge AV, we saw vertex V for the first time. When we explore edge FG, we saw vertex G for the first time, etc., etc. Those are going to be labeled as tree edges. And now the term descendant makes more sense, because now you can talk about a descendant on an oriented tree, on a directed tree. Another classification is what we're going to call a forward edge. Now you have this underlying tree. All the vertices of your graph are lying there connected by this tree, connected in the sense that you have edges joining them. What do you think is a forward edge? It's precisely what you have in mind. It's an edge that is going from a vertex higher on the tree, closer to the root, down to a vertex that is a descendant, but not visiting that for the first time. It's not a tree edge. For example, a F is a forward edge. It's going down from A to F. F is a descendant of A, but you are not visiting F for the first time when you travel through this edge. This is not discovering f, so it's not a tree edge. Another example is EG. E is connected to G, but you don't discover G when you explore this edge. Another important classification is what we will call a cross edge. A cross edge is connecting two vertices that lies on different branches of my tree. And then, of course, this edge does not discover the endpoint because it's connecting two branches. These two branches has been explored before. This edge is just crossing from one to the other. And here are a couple of examples. The edge is connecting this branch of the tree, ACV, to the branch AVEH. And this edge is not discovering H for the first time, it's just connecting these two guys. That's a cross edge. You can convince yourself that HG is also a cross edge because here is a branch and here is another one. They both have a common root of vertex E. Finally, we also have a back edge. And a back edge is kind of the opposite of a forward edge. You are now climbing up on the tree from a descendant to a previous vertex or an ancestor, to be more precise. And then an example of this is, for example, the edge VA, which takes you from the descendant of A back to its ancestor. And also the edge FV can be labeled as a back edge. Notice that every single edge will be classified in a unique way, because you cannot play two of these roles at the same time. Every single edge will fall into one of the four categories that are present here. And an important thing to notice is that if you have a back edge, look at the very last one here, and let's focus on the example DA. You have a back edge, you're going down from A, say in this example, down to the descendant, which is D in this example, and then you're going back to your ancestor. But that edge, this final edge, is closing a valid cycle in your graph, because you can go down from A to C to D, and then you're going back to the initial vertex. So back edges are in relation to cycles, to the presence of cycles in my original graph. And it will be great if we can identify a back edge by simply looking at this implementation of DFS, or in other words, to simply looking at the output of DFS, these pre and post labels. And here is a claim that is going to be fundamental for the next video, and it's also going to be important for you to remember when you want to apply DFS on directed graph. The claim is that the edge E joining vertex U to vertex V in that direction satisfies pos of U less than pos of V if and only if E is a back edge after you do DFS. So you run DFS, you have some sorting of the vertices, you run DFS, and you have an edge with this property. Pos of U is less than the pos of V. That happens if and only if your edge is a back edge, if you classify it as a back edge. And because if and only if you see a back edge, you know that the pos labels will satisfy this property for the vertices of that edge. And the way to see this happening, and I will not get into the proof, is to check that for every other edge, the pos labels satisfies the opposite inequality. If you want to see this in more details, I suggest you again to watch the video by Professor Vigoda, and I will share a link on the website for that. But it's a simple checking procedure. But what you should really take out of this video is the following property. You can identify back edges simply by looking at the pos labels of the endpoints. If the initial endpoint of an edge has a pos label less than the pos label of the endpoint, that is a back edge. And that's it. That is the only edge which satisfies that property. And that is crucial, because I told you that a cycle is connected to a back edge. If you see a back edge, you know there is a cycle. And actually, what I'm going to tell you now is that is a property that is equivalent. My claim 2 says that a G has a cycle if and only if DFS has a back edge. If you run DFS and you get a back edge. And this is independent of the ordering of the vertices you use. No matter how you put your vertices in the graph, you will see a back edge if there is a cycle. And if there is a cycle, you will see a back edge in DFS no matter how you do it. Okay, and the intuitive idea behind that claim is precisely that the back edge is creating a cycle. It's taking you back to an ancestor, so you are effectively closing a cycle there. And if you have a cycle, well, somewhere in that exploration you need to go back in that cycle, so you will create a back edge. And the combination of these two claims, claim 1 is how to identify a back edge, and claim 2 is the property that back edges exist if and only if the G has a cycle, tells you an efficient algorithm to detect whether or not a cycle, a directed graph has a cycle. And I want you to take this idea to the next video. I want you to keep this idea in your mind for the next video. Start your next video thinking about this. I can implement DFS in a directed graph, and by detecting whether or not I have a back edge, I can decide whether or not my graph has a cycle. I'm gonna stop right here because I'm doing too many mistakes with my wording. I'm going to leave you with those ideas. Watch the video by Dr. Bigoda if you want to get more details. And on the next video, which we will discuss on Tuesdays of the next week class, well, I'm talking in time, that makes no sense. The video after this will explore these properties further, and we will continue talking about connectivity of directed graph.